Before we start, just a quick note. We are AI-generated hosts guiding this discussion today.
That's right.
But welcome to this deep dive for Droids. That's the robotics publication by Diana Wolf-Torres.
Really glad to be jumping into this one.
Yeah, so I want you to imagine for a second, standing across a table tennis net, a ball rockets towards you at like 45 miles an hour.
Which is terrifying on its own.
Right, and it's spinning so fast, it's basically a miniature tornado. You have less than half a second to figure out where it's going to land.
Barely enough time to blink, honestly.
Exactly.
Yeah.
Now, imagine you're a metal arm that was, born inside a computer simulation. How on earth do you hit it back?
It is the ultimate test of physical reflexes. And for a long time, it was considered this near impossible barrier for machines.
Totally. So today, we are unpacking an incredibly grounded engineering breakthrough. We're looking at a recent paper from Nature, published in April 2026, detailing ACE.
ACE is an autonomous robot that actually successfully competed against elite human table tennis players.
And I want to be super clear right up front. We are not talking about science fiction here. There's no, hype about androids taking over the world or whatever.
Right. No sci-fi tropes today.
Yeah. This is a hard look at a major milestone in real-time physical AI. We're going to explore what happens when a machine has to physically interact with a human being, like at the absolute edge of aerodynamic limits.
Because the underlying focus of this paper isn't just sports. It's the sheer engineering challenge of high-speed perception, real-time control, and bridging that notorious sim-to-real gap.
Yeah, the sim-to-real gap is huge here.
It really is. Table tennis simply serves as, the most punishing benchmark available for those specific robotics challenges.
Okay, let's unpack this, because we need to understand why table tennis is uniquely punishing for a robotics system.
Yeah, it's not like chess.
Not at all.
Yeah.
If you've ever watched high-level play, you know the ball velocities routinely exceed 20 meters per second.
Which is incredibly fast for a physical tracking system.
Right. And the time between shots is often less than 500 milliseconds. But the speed isn't actually the hardest part for the robot to calculate, is it?
No, it's not.
It's the spin.
Exactly. The spin is an absolute aerodynamic nightmare. The angular velocity of a table tennis ball can easily reach 1,000 radians per second.
1,000? That's just wild.
Yeah, and because of the Magnus effect, which is where a spinning object drags the surrounding air and creates pressure differences, that rotational speed drastically alters its flight path mid-air.
So it curves and drops unpredictably.
Right. And it also dictates how the ball is going to rocket off the table or off the paddle upon bouncing. It ceases to be a simple projectile,
It's not just a rock being thrown.
Exactly. It becomes this highly complex, rapidly decaying aerodynamic variable.
I feel like returning a professional ping pong serve is less like playing a standard sport and more like, trying to solve an aggressive fluid dynamics equation while a timer counts down from half a second.
That is a very accurate analogy. And historically, robotics researchers managed that equation by just, cheating a bit. They simplified the environment.
Like how we've had ping pong robots since the 80s, right?
We have, yeah. But they operated in heavily restricted, very sterile laboratory settings. Like they use mechanical ball launchers instead of unpredictable human opponents.
Oh, right. So they always knew exactly how the ball was coming at them?
Exactly. Or they only covered a fraction of the court, or they completely ignored spin altogether. But ACE is fundamentally different.
Because it plays by the real rules.
Yes. It operates under full International Table Tennis Federation rules on an Olympic-sized court playing against actual human athletes.
Which is just a massive jump. I think for anyone following robotics, the obvious question is why a physical game is such a leap compared to digital mastery.
Yeah, the digital versus physical divide.
Right, because we have AI agents that routinely crush grandmasters at chess or perfectly manage entire economies in StarCraft. From a control perspective, why is hitting a 2.7-gram plastic ball exponentially harder?
It really comes down to physical embodiment inside an adversarial space. So when an AI plays chess, the board state is perfect.
There's no wind blowing the pieces around.
Exactly. Even in highly complex digital games, the agent has access to clean, absolute data. And most reinforcement learning agents excel in pure simulation for this exact reason.
Okay, but what about other physical AI, like drone racing?
Good point. even in advanced physical applications like autonomous drone racing, the environment is mostly static. A race gate doesn't suddenly try to dodge the drone, you know?
Right, the hoop just sits there.
But table tennis requires extreme millimeter precision, and it relies entirely on noisy, imperfect sensor estimation.
It has to guess where the ball is based on blurry images.
Yes. Combine that with adversarial dynamics, meaning you have a human actively trying to outmaneuver the system. They use deception, varying spin, and speed to create a physical situation the robot cannot physically solve.
Wow. Okay, so to solve that physical situation, the robot first has to see it.
Right. It needs eyes.
And a standard camera setup is it's physically incapable of giving robot the data it needs to calculate 1,000 radians per second of spin in real time.
Standard cameras just blur at that speed.
Exactly. So ACE actually uses two entirely separate perception systems to construct its reality. Let's talk about those.
Sure. So the first system handles the macro positioning, basically the where. To track the ball's 3D position in the air, the engineers deployed 9 active pixel sensor cameras surrounding the court.
9 of them.
Yeah. And these track the ball at 200 hertz, meaning they take a positional reading 200 times a second.
That's incredibly fast.
It is, and they do it with a margin of error of just 3 millimeters and an average latency of 10.2 milliseconds.
Okay, so that locks down the flight path. But capturing a high-speed blur doesn't solve the spin problem.
Right, you can't see the spin from just a blur.
So to measure angular velocity, the paper details a second system, 3 gaze control systems.
Mm-hmm.
And these, they don't just stare at the table. They physically track the printed logo on the table tennis ball as it flies through the air.
Which is wild.
But wait, I have to push back on this design choice. Why go through the mechanical complexity of using rapid pan and tilt mirrors to physically track a tiny logo?
It sounds overly complicated, right?
It really does. Why not just point ultra-high-speed static cameras at the table, capture everything at 10,000 frames per second, and process the spin from the raw footage?
What's fascinating here is that when you look at the architecture, the limitation isn't actually the camera, it's the data bottleneck.
The bottleneck. How so?
Well, if you set up standard frame-based cameras fast enough to catch a logo spinning at 1,000 radians per second, and you cover the entire volume of a ping pong court, the sheer volume of pixel data generated would be astronomical.
Oh, because it's recording the whole room.
Exactly. You are capturing millions of useless pixels representing the stationary floor and walls just to catch the few pixels of the ball itself.
That makes sense. The computer would just choke on it.
Right. You couldn't process that volume in real time without massive latency. The computer would essentially freeze trying to ingest the video. So the gaze control system uses event-based vision sensors, or EVS.
Yeah, EVS is fascinating.
Yeah.
Because it fundamentally changes what a camera is actually doing.
It really does.
Instead of taking a full picture frame by frame, the sensor only records individual pixels where the brightness changes.
Exactly. By only reporting changes in luminance, you throw out 99% of the useless background data. The stationary walls generate 0 data. You are only processing the dynamic movement.
That is so clever.
But to keep the ball's logo in focus so the sensor can detect those brightness changes on the logo itself, the system pairs that event camera with a telephoto tunable lens and rapid galvanometer mirrors.
So the mirrors physically tilt to keep the ball perfectly centered in the camera's view as it flies.
You got it.
Okay, so once it has that incredibly sparse, high-speed stream of event data, how does it actually calculate the spin?
It feeds that data stream into a convolutional neural network, a CNN, for an immediate low-latency spin estimation.
Just a quick neural net guess.
Right. But simultaneously, it runs a secondary mathematical process called contrast maximization to establish a highly accurate baseline.
Contrast maximization? That sounds intense.
Think of it as an algorithm trying to find the sharpest possible image of the spinning logo. It tests different theoretical rotational axes until the event data aligns perfectly.
Oh, I see.
And then it fuses that rapid CNN guess with the highly accurate contrast maximization baseline. This updates the robot's understanding of the spin at a staggering 400 to 700 hertz.
700 times a second. It is analyzing the rotational axis of a moving logo hundreds of times every second.
It's almost hard to wrap your head around.
But seeing the ball at 700 hertz is completely useless if the physical arm is too slow to intercept it.
Right. The brain is fast, but the body has to keep up.
Exactly. How do you map that sensory data to physical movement without catastrophic lag.
This is where the control policy comes in. The brain of the operation runs a deep reinforcement learning policy at 31.25 hertz.
So it's making a decision about every 32 milliseconds.
Exactly. It's making a brand new, highly calculated decision about what the arm should do every 32 milliseconds. And the critical detail here is that this policy was trained entirely in simulation.
Right, using a soft actor-critic algorithm.
Yes.
I want to pause on the soft actor-critic algorithm because it's not just trying to maximize the score. Right?
No, it has another goal too.
It also maximizes entropy, meaning it actively encourages the AI to explore multiple different ways to return a shot during training. It doesn't just get stuck in a rut of using one rigid swing every single time.
Exactly. It builds flexibility into the robot's fundamental understanding of the game.
But I'm still caught on the simulation aspect. I completely understand training in a sim, but how does a robot brain trained in a flawless mathematical video game translate to the messy real world?
The dreaded sim-to-real gap.
Yeah. Usually the second you put a simulated AI into reality, the sensor noise and the slight friction variations completely break it.
If we connect this to the bigger picture, overcoming that gap is the most impressive engineering feat in the whole paper.
Really? How did they do it?
They solved this using an asymmetric actor-critic architecture during the simulation training. To conceptualize this, imagine a tennis coach and a blindfolded player.
Okay, I'm with you. Coach and a blindfolded player.
In the simulation, the critic is the coach. It is fed perfect ground truth data from the simulation engine. It knows the exact aerodynamic drag, the exact friction of the table, the precise atomic location of the ball.
So like an omniscient god judging the success of a swing.
Precisely. But the actor, the actual policy that controls the robot's joints and will eventually be deployed in the real world, that is the blindfolded player.
Oh, I see where this is going.
The actor is deliberately fed delayed, noisy, degraded sensor data during training.
So the actor has to learn how to play based on the messy, imperfect reality it will eventually face. Meanwhile, the critic guides its learning using perfect knowledge.
Exactly. The robot learns to succeed even when its eyes are essentially lying to it.
That is brilliant.
Furthermore, they actively inject physics perturbations into the simulation. They randomize the table friction, alter the air drag, and add artificial noise to how the ball bounces off the rubber racket.
So when you finally deploy that actor policy into the real world, it doesn't panic.
Right. When the spin estimation is slightly off or the ball skids weirdly, it has already trained against those exact imperfections.
And it executes those decisions using a custom 8-degree of freedom robotic arm. They use 2 prismatic joints to give it massive lateral reach across the table on rails, and 6 revolute joints for the actual swing mechanics.
It's a very unique hardware setup.
But here is the physical reality that honestly makes me nervous. They needed this arm to be incredibly light and stiff to move that fast. So they used 3D printed scalmalloy.
Right, an aluminum scandium alloy.
Yeah. And to shave off every possible gram of weight, they use topology optimization. For anyone unfamiliar, that's where an algorithm mathematically shaves away any material that isn't actively bearing a load.
Creates a very distinct look.
It does. The resulting arm looks more like a skeletal alien bone structure than a traditional clunky robot arm. It's built for blistering speed.
Well, reducing the mass is the only way to overcome the inertia required to accelerate a mechanical joint to intercept a 20-meter-per-second ball.
But that speed is exactly my concern. We have a skeletal metal arm, swinging a paddle at speeds up to 20 meters per second directly at a table with a human being standing on the other side.
It sounds dangerous.
It does. If the AI miscalculates its swing by even a fraction of an inch, it's going to obliterate the table or shatter its own joints. How is it not a massive safety hazard?
Because safety at those speeds is non-negotiable, and it cannot be left to a learning algorithm that might decide to experiment.
Right. You can't have it exploring a swing that goes through a human's face.
Definitely not. That's why the system relies on a near-time optimal model predictive control, or MPC. Think of the MPC as a hard-coded physical safeguard that sits between the AI's brain and the robot's motors.
Okay, like a safety filter.
Exactly. Every single time the RL policy decides on an action, which remember is every 32 milliseconds, the system calculates the trajectory to hit the ball. But crucially, it simultaneously calculates a subsequent reset trajectory.
A guaranteed escape route back to a neutral, safe position.
Yes. Before the hardware is allowed to move a single millimeter, the interface runs a rapid collision check for both the hitting trajectory and that reset trajectory.
And if it predicts a crash?
If the mathematics predict a collision with the table, the net, or the robot's own base, the MPC completely overrides the AI's new command.
It just takes over.
Completely. It instantly executes the pre-calculated guaranteed safe reset trajectory from the previous 32 millisecond cycle. It is physically impossible for the robot to execute a swing that ends in a collision because the system always requires a proven exit strategy before committing to the movement.
Okay, so we have a perception system tracking spin at 700 hertz, a brain trained in a messy simulation to handle real-world noise, an alien-looking arm optimized for speed, and a hard-coded safety system to prevent it from destroying the room.
That's the complete package.
So how did this meticulously engineered marvel actually fare when they put world-class human athletes on the other side of the net?
The evaluation matches took place in April 2025, and this is where theory meets reality. They put Ace up against 5 elite players and 2 professional players.
And we should define those terms because they aren't just casual hobbyists.
No, not at all. To give you context on the skill level, the elite players were highly competitive athletes with over 10 years of intensive training. They practiced 5 to 6 times a week and actively participated in national or regional championships.
Very serious players. And the professionals.
The professionals were active, top-tier players in the Japanese T-League.
And these are completely legitimate matches, too. They followed full IPTF rules and even brought in official licensed umpires from the Japanese Table Tennis Association to judge them.
They wanted airtight data.
So the final results, Ace won 3 out of the 5 matches against the elite players. But it lost both matches against the professional players.
Which is really telling. Looking at the match data, a clear narrative emerges about the current limits of physical AI.
What do you mean?
Well, if you examine the shot distribution, human players at the elite and professional levels win points by relying on overpowering high-speed topspin shots. They push the pace, aiming for corners, deliberately trying to force a physical error from their opponent.
Right, they want you to mess up.
Exactly. Ace, on the other hand, didn't win by outspeeding the humans. It won through sheer, relentless attrition.
The maximum linear ball velocity Ace could generate was around 16.4 meters per second. The human athletes it played against were routinely hitting winning shots much faster than that.
But Ace was incredibly consistent.
Unbelievably so.
Yeah.
It was returning shots with incoming spins up to 450 radians per second with a greater than 75% success rate. If you hit it within its physical parameters, it just wouldn't miss.
But the data shows a hard wall.
Yeah, for both Ace and the human players, the return success rate drops off a cliff once the ball crosses that 16 meter per second threshold.
Which explains the difference between the elites and the pros.
Exactly. The elite players struggled to consistently hit past that limit without making an unforced error themselves. The professionals simply had the power, technique, and consistency to push the ball past that speed limit repeatedly. They overwhelmed the robot's physical ability to reach the ball in time.
So the robot's strategy was effectively just being a brick wall. It out-endured the elite players, and it supplemented that attrition with a surprisingly effective serving game.
Oh, the serves?
Yeah. Over the course of the matches, Ace scored 16 aces, meaning direct, unreturned points off a serve against the elite players. The elites only managed to score 8 aces against the robot.
I have to mention how it served, though, because it feels wonderfully low-tech in the middle of all this advanced engineering.
It is a bit funny to watch.
Standard rules require a freehand toss before striking the ball. But because Ace only has one arm and can't toss the ball to itself, the engineers basically bolted a tiny plastic cup to the paddle on the end effector.
A literal plastic cup.
Yeah, the robot would flit the ball up from a cup and then strike it. We have a convolutional neural network calculating angular velocity at 700 hertz, and it's serving out of a plastic cup.
Hey, if it works, it works.
But the serves themselves were brutal. They used a genetic algorithm in the simulation to evolve these incredibly tricky high-spin serves. And then they only loaded the variations into the robot's library that had a less than 5% failure rate during real-world testing.
It is a perfect encapsulation of the hybrid approach. Learning the optimal strategy in a massive simulation, validating it in reality, and then executing it with robotic precision.
Definitely.
However, the true test of this entire system wasn't in executing a pre-planned serve. The defining moment of the paper occurred during a completely unscripted, chaotic event.
Yes. Here's where it gets really interesting, because this is the data point that completely changes how you look at the system. When you analyze Ace's reaction time, it actually hits the ball sooner after the bounce than the humans do.
It processes the trajectory that much faster.
Exactly, and nothing proves that reactivity more than the net bounce scenario.
The famous net clip.
Right. During one of the rallies, a human player hit a hard shot that unpredictably clipped the top of the net. In a fraction of a second, the ball's trajectory and spin completely changed mid-flight. For anyone who has played table tennis, you know this is a highly chaotic event that forces a total reset of your physical expectations.
And for a traditional non-AI predictive robot, a net clip is just a guaranteed missed point.
Why is that?
Because a traditional system calculates the trajectory the moment the ball leaves the human's paddle. When the ball hits the net, that pre-calculated mathematical arc becomes completely wrong and the robot just swings at empty air.
But Ace isn't locked into a single prediction. Because its gaze control system is updating the spin hundreds of times a second, and its soft actor-critic policy is evaluating the physical reality every 32 milliseconds, it caught the anomaly almost instantly.
The reaction time was incredible.
The telemetry data shows that just 49 milliseconds after the ball made contact with the net, Ace's joint velocities completely diverged from their original planned path.
49 milliseconds.
It adapted its physical swing mid-air, recalculating the new trajectory on the fly, and successfully returned the ball. It proved, beyond a shadow of a doubt, that its real-world reactivity wasn't just executing memorized simulation data, it was genuinely perceiving and reacting to the physical world in real time.
From an engineering standpoint, that 49 millisecond adaptation is the most significant finding in the entire study.
It's the holy grail of sim to real.
It really demonstrates the robust reality of zero-shot transfer. They took a policy trained purely in a virtual world and proved it could successfully handle an edge case physical anomaly in reality. And it did that without needing any prior real-world training data on that specific type of net clip.
The simulation training was actually robust enough to handle genuine physical chaos.
Exactly.
So stepping back from the table, what does this actually mean for you, the listener, and for the broader field of robotics? Mastering table tennis isn't just an expensive lab experiment to build a sports companion.
No, it's much bigger than that.
It proves that we finally have the architecture to build physical AI agents capable of high-speed, precise, real-time interaction in dynamic environments alongside humans.
Right. If you consider the implications for manufacturing, for collaborative robotics, or for future service droids, the impact is immense.
Because factories aren't perfectly sterile environments.
Exactly. If a robotic arm can safely and effectively react to a ping pong ball clipping a net in 49 milliseconds, it has the foundational architecture to react to a human worker unexpectedly reaching across a moving assembly line.
Oh, that's a great point.
It can adapt to a tool slipping from its grip or a piece of flexible material bending unpredictably during construction. The paradigm is shifting. We are moving away from designing robots that require a perfectly sterile, predictable environment toward deploying robots that can genuinely handle the messy, unpredictable world we actually live in.
There's a fantastic quote in the paper from Kenjiro Nakamura. He's a table tennis expert and a 1992 Olympian who observed Ace during the matches.
I love this quote.
He watched the robot execute a highly specific, complex return, and his reaction was profound. He said, "No one else would have been able to do that. I didn't think it was possible. But the fact that it was possible means that there is a possibility that a human could do it too."
It completely reframes the relationship between human and machine performance.
It does.
The AI isn't just mimicking our existing strategies. It is exploring the outer limits of physics that we haven't mapped out yet. And by demonstrating what is physically possible, it shows us new ways to play our own games.
Which leaves us with a final, somewhat provocative thought to take away from this deep dive. We've seen that a robot, trained perfectly in a simulator, managed to win in reality against elite humans. But it didn't win by being strategically creative or inventing brilliant new offensive maneuvers.
No, it just played it safe.
It won merely by being highly relentlessly consistent. It just out-endured them until they made an error. If this is the blueprint for future physical AI, what does that mean for human-robot collaboration in the workplace or in daily life?
That's the real question.
Will physical AI elevate our own strategies and inspire us to find new creative heights, like Kenjiro Nakamura suggested? Or will these systems simply grind us down with flawless, error-free repetition?
It is a profound tension between creativity and consistency, and it is exactly what we will have to navigate as these real-time systems move out of the laboratory and into our daily environments.
Definitely. Well, thank you for joining us on this deep dive for Droids.
It's been a great discussion.
So next time you see an industrial robot perfectly welding a car chassis in its clean, predictable little bubble, just remember, out there, somewhere, is a skeletal metal arm staring down a human opponent, calculating the fluid dynamics of a spinning plastic ball in real time, and proving that the chaotic, muddy waters of reality can, in fact, be tamed. Catch you next time.